So, let us start lecture number 2 of this module 6. And the previous lecture, this lecture number 1, I discussed the AC power flow, and also I discussed the various type of AC DC power flow, and we discussed about the sequential, unified, including the variable elimination method and the extended variable methods. Today I will be discussing about these methods in detail, and before going for this in the sequential method or any method, these are the 5 basic equations. Those are already we have derived while discussing this HVDC course. Only difference here you will find that some of the terms, the coefficients are not matching. For example, if you will see the first here is coming something else rather than the previous one. If you remember, I wrote the equation that is the VD, that is your 3 under root 2 EM over pi, here cos alpha minus your RC into ID. Oh, sorry, yeah, 3 root 3, yes, sure. So, we wrote this equation, we derived also. Now, you will see here is slightly different than what here I have written. We wrote this EM in the sense that if you see your HVDC link, here let us suppose this is your rectifier. Here we are having a transformer, and this transformer is your OLTC transformer, that is your online tap changing transformer, and here is your this. So, this is 1:AR I am writing. I am writing from the rectifier side. So, R represent rectifier. Whenever I am using here I is used for inverter, right. So, this is your VDR which is written here in this expression. So, this D here is the DC and R for the rectifier. Here we are having the resistance of the line RD, and here this side we are having your inverter, that is here it is I can write VDI, and we are having again the OLTC transformer. In this case we are having AI is to 1, and your the VTR which it is used here, T is the terminal voltage, R is your rectifier terminal voltage. Here I am writing VTI. Well, now this expression is written if this voltage we are talking here, if some voltage are here, but we are now representing this side here because we want that this transformer should be on the DC calculation rather than AC calculation. The reason for this tapping, that is why I am writing 1:AR. So, tapping this side, so it is keep on changing, it is just a part of controller. If you remember HVDC, because here if the firing angle is hitting, we can use this controller as well. So, if you are using in the AC power flow, your Y bus matrices keep on changing. So, we do not want this, and that is why here we are keeping this side, because anyway we are solving the DC equations. So, this part we are trying to keep in the DC side, and AC side this terminal voltage here, because your network topology is fixed, your matrix is fixed, and there is no problem. So, that is why you can see here the tapping it is represented in the DC side here, here also I am representing this side. So, this is the reason we represent this OLTC in this way for the solving our AC DC load flow. Now, this equation which we have written now, this is your peak. If I write in terms of some voltage V here, that is RMS, then it will be under root 2 times V. The peak value is RMS value here. Now, I am writing any V here, we are getting this value. Now, still we are not getting the expression. Now, this V is here we are talking. If you are transforming this side, it is going to be your AR VTR. Still we are, there is one term missing here under root 3. You know, once we are writing the equation, the line to line voltage we are taking here, because in the other power flow your base, even though we take the line to line voltage. So, this basically goes off, and this equation we are having here. Only difference here RC XC, you can represent here XC, you will get here 3 XC upon pi, and that is the equation here 1. So, this equation is, you can say, the similar to here. So, alpha here also I have written in this one is for rectifier R. So, it is clear for this end? It is. Now, we are getting, means now your this voltage whatever we are writing, it is your line to line voltage, and this V d is as usual DC voltage. So, this is similar to this, no need to explain. This equation is a simple basic circuit equation. This voltage will be the drop here if current I d is flowing here. So, this will be equal to this plus this voltage which is written here. I d is the current. This equation is the real power which is flowing here, this voltage multiplied by this, and the real power here, this current multiplied by this voltage is your, this is the I for inverter, it is written. Now, these are the 5 basic equations, but out of this 5, only your 3 are the independent equations, because these are related to here itself. So, these 3 will be using every time. These are the basic DC equations that should be solved depending upon your control modes. I will come later on. Now, let us see this one. Here also, if you will see this IAC I am writing, it is, we have proved this is AC. If you remember, it was under root 3, under root 2 means I wrote under root 6 divided by pi IDC. We have already proved this. This we have derived under root 6 if you remember. The K term here, and this was the case when it was the ideal, means only the 2 valve operation. So, we are using a word one term I can say K due to the overlap. Once this overlap is there, due to this, the value of this value here is going to reduce, because if not overlap, you remember here this is like this your current in this here. So, we are getting here like this. If there is some here overlap, then its value is going to be reduced slightly, and that factor here is used as small k. But still again the coefficient is not matching. Is matching? Is not matching, because there is under root 3 terms again here is missing, means extra under root 3 is coming just like here. But the DC current here, this current, line current or phase current is same, because it is not voltage. But this is represented in terms of, if you are writing in terms of per unit, then it will be the different. Now, come to the first per unit, then we will derive here why we are getting, means our aim should be here 3 under root 2 divided by pi ID, K will be there, IC. We want this in the PU system. To see this, here let us see this slide. What will be the base quantities? You know this base quantities in the AC system, 3 phase if you are talking. So, power we normally take this SB. Here I am writing if top, so it will be taken here SB. This is the AC power. So, AC power will be equal to your the DC power, and here it is I am writing the DC B. Only the difference icon you can write AC here hardly matter, it's just for the notation I am using. So, the AC and the DC power we are taking the same. The reason is true, because whatever the AC power here 3 phase is coming, here the 3 phase is going, even though your system is lossless here, it is completely going there. So, the base power here for AC and DC we are taking same. Now, come to the voltage base. Here we take this voltage base here, it is nothing but your line to line voltage. Now, this voltage is no doubt is the line to line voltage, line to line AC voltage. So, if you are writing this VDC base, option can be, we can take this base is similar to your, this is your AC base, we can take. Now, this one base you are fixing, here you cannot fix it, because your current is also changing. So, normally what we do, this base you can take equal or you can take in terms of bridges. So, what we do here, we write a capital term K, because either you can take 1, if you see here, then your DC base voltage, this voltage and this voltage here, the line to line is equal to this. So, the current base will be correspondingly changed. You know the voltage base keep on changing throughout even the AC system as well due to the transformation. Here also you can change the, even though this base here equal, or you can change any value depending upon the number of bridges here. Normally it is convenient, we take either same, so calculation becomes very easy, or you can take here this term, if you remember this is terming 3 under root 3, it is basically this term was appearing. So, that term you can take the number of bridges, because you are having so many number of bridges. So, you can you just calculate and then you can multiply it by the number of bridges. So, then you can equate in that fashion. So, either you can take 1 or you can take this, for it is a simplicity in the calculation, nothing else. Normally, we take k is equal to 1, it is very simple. Now, once you are taking k is equal to here this unity, means this base is equal to this base. Now, if you will see the AC base, the current, now I want this AC base, it is nothing but your S base divided by under root 3 B base. In the 3-phase system, this base is basically calculated fixing the 2 only, because if the 3 quantities, one is dependent. So, you have to fix 2, for third will be calculated automatically. Okay. Now, because it is the 3 here line to line, the power here is, we write S is under root 3 VL IL. So, this is, we are taking line to line, then it is under root 3 here. If you are taking phase here, so it is 3. So, this is coming. It's now, I want this, what is the DC base now? This base, just you can see your here, and we will find that we can calculate this will be your under root 3 IB base. Why? This you can put this DC equal, this voltage you can fix that value, and this divided by this is your ID base basically, and you will find this value here. Not clear? Let's just put it here. You are getting this base is your DC base, this is equal, here under root 3, here VDC base. The power here, the current, this is nothing but ID base, because the power divided by voltage, here the power is equal to VD into ID. So, here you can say this is multiplied this side, means IDC base here is this term, and you can see this under root 3 term is appearing here. Now, I will go back here. If writing in the per unit here, then you are dividing by here IB base, here you have to divide by ID base. So, then this we are putting ID base here, under root 3 term will be going up, and this 3 will be coming here, and that is why this is here. So, the previous equation is valid if you are writing in the per unit here. This equation here, this 3 under root 2 term is appearing. It's clear? Okay. Now, here these are the basic 5 equations. Now, we have to go for the sequential method, and let us see the flow chart. As I said, in the sequential load flow methods, we solve first AC, then we go for DC, AC, DC and DC, always AC, DC, AC, DC, AC, DC, and finally, we will get the converse solution. But it is not so simple like AC, DC. You have to see, we require something, we have to calculate the something stopping criteria, sometimes you have to calculate some variables, because if you are calculating the AC load flow, you are getting this voltage. If you are solving this, this may not be mismatching, because this is related to the VDR. So, what we do, first no doubt we have to have the input data, means whatever this parameter of the DC as well as the AC, then initial conditions for the AC as well as the DC you require, because you are having the nonlinear set of equation 1, 2, 3 where the nonlinear equation, because cos alphas are there. Then you have to solve the DC equations, the first to 3, 1 to 3, you will get the VDs, this IDs and the PDs etc. you can calculate. I will come later on what are the variables. In these 3 equations you will find there are 7 variables. Go back again. Here if you will see this, here in this complete 3 equations you are having the 7 variables, and your variables are, you see this, what are the variables? Your this VDR, you are having VDI, you are having alpha R, you are having gamma I, you are having AR, you are having AI, you are having VDI I have written. RD is constant, the parameter. ID, yeah. So, you are having 7 variables and you have only 3 equations, you cannot solve it. You have to set 4, then only you can solve it and you can get the unique solutions, because we require number of unknowns should be equal to number of equations. Now, this is called XDC, these are the DC variables. Having 3 equations, we are having the 7 variables. So, normally I will show you later on what we do. Out of this 7 we fix 4. Why? Because you know the control modes how they are working. Now, the control characteristic is coming into the picture. Based on its operation, whether inverter is controlling your current or voltage, and in vice versa, one will be controlling voltage, one will be controlling current. Based on that, few things are fixed and remaining things are calculated. So, here only we require 3 unknowns, others are fixed in that particular control modes. So, based on that given values we are going to calculate. So, I will come back again in that flow chart. We are solving these equations for given, I will come to the control modes later on, even though in the next slide. So, we are solving the DC variables and we can get it here. You can say we are getting VDs, IDs, and we are also getting the VDI, then we are getting the PD, means we can calculate here these variables based on this solution. Now, then we determine the power factor angle. Once you have determined this DC variable what the power is going, we can now calculate what will be your power factor angle, and you know the power factor angle is cos phi is approximately equal to your cos alpha plus cos delta by 2. This equation also we have brought it, normally it is approximately equal. So, the power factor angle we determine, because alpha may be unknown, by solving you can get the alpha depending on the control modes. So, here also u is there. So, all involved here we are just getting this, means you can calculate u also based on that equations. So, calculating this you are just calculating the power factor. Why the power factor? Because at this pulse we only have the real and reactive powers, because what is the load here it is going, it is your P and it is your Q. P is basically same, we are assuming if it is lossless, we normally assume the lossless and we take it. So, the P is same, we require Q, and for Q we require the power factor. So, here the power factor is dependent, then you determine P and Q loading of the DC system bus. As I said, we had required this P and Q, because this P and Q require in your AC load flow, because if you are, what we do, this DC we take as a load here P and Q and solve our AC network, because in AC load flow you require P and Q at any bus, that you can just calculate it. In the DC we can calculate this from the solving this DC equations. So, once you are just after power factor, the P and Q loading of the DC system, once you have calculated here the fourth state, then you have to solve the AC power flow. Means first we solve the DC, then we are going for the AC with the initial guess again. So, then you are calculating, solving this, what is happening? Now, you are getting the different ATR. Once you are solving this as a load, this whole AC load flow, this voltage will change. So, now it is a load bus, because your initial guess is not perfect. If it is perfect, you will get the same maybe. Here also we had the initial guess and solving this nonlinear equations 1, 2, 3. So, it will be certain different. Then what we are doing, once you are here calculated the VTR, and before that you assume certain value here, what was this VTR? You will take the ratio, the tappings will be changing, because based on that whatever you have taken the initial guess of the taps, based on now this VTR you are getting different, means your tap position is going to be changed. If it is same, means tapping is same. So, once it is same here, then this is a solution, no need to go further, because here already you have solved and everything is clear now, the power is flowing. But if it is not so, then you have to adjust your the DC variables here, the voltage, and then again keep on repeating, so that you can get the tappings as well, the constant. So, this is your sequential load flow. In this you have to solve the DC equations, go for AC again, then DC, AC, and finally you will get the converse solution.
So, inverter must be treated as a generating unit is connected like this?
I will come again here. This is your the P with the negative load, and this is your Q. So, this is also a load bus with the negative power, nothing else.
By solving the DC network, we
will get the P and Q here. Again the power factor here also means similar to this, only the direction of P is here changed. Here you are taking as a PQ load, both are going away, means as a load. Here is a negative load. In fact, if load you are taking, the bus is coming out, you load as a positive, this is a negative P. Q will be in the same direction. This will be more clear when we are going to combine the AC DC together, then certainly the P will be coming into the picture. Yeah, now here you can say what is this bus? It may be a generator bus here, huge generator, it may be hitting its limit. Again the Q you have to verify whether it is a generator bus or not. If generator bus, the voltage is same, this side, that shadow is there, so this is a DC solution, no problem, because the voltage is maintained, the reactive power it is giving, reactive power will be taken, this will now vary, the power factor will be changing, nothing else.
In that case, P will be specified
here. No, if it is generator bus, here the P, because whatever the P is going, P you know, you have to write the P equation in the AC as it is, no difference. Whether you are taking as a load bus or generator bus, it depends upon whether you are having a generator or not. If you are having a generator, you can take as a generator bus, this will be the negative load at this, and then you can solve it. And you have to check its reactive power generation, what is the reactive power taken, and this like similar AC load flow, no change at all. Only here you have to take this DC system equivalent to the PQ load, nothing else. Here also you have to take this P is a negative and this is Q is a DC. You can say the load, the DC system is just represented as equivalent real and reactive power loads, nothing else. Now, let us go to your extended variable method. In the extended variable methods, normally what we do, we use the Newton-Raphson method, Newton-Raphson method in the polar coordinate. It is very easily we can incorporate it, but we have to go for the, in the Newton-Raphson load flow, we write the power mismatch equation. Now, I can remove this because it's we are not going to use. You know this in Newton-Raphson method here, it is your P, it is your Q. Already I just reviewed it in our previous lecture, that is lecture number 1. Here I am using the delta, here I am using del V by V, here we are having the Jacobian. This is your Newton-Raphson load flow methods in polar coordinate. So, you can see in this equation, if you are going to include your DC here, and now I am talking the extended variable methods, means we have to extend it, we have to extend the variables here corresponding to your DC. Now, if you are going to extend it here, now we have the 3 DC equations, as I said, the basic 3 DC equations 1, 2, 3, that was your, here it was your R I am writing, means we are having R1, R2 and R3 3 equations. Here it is again the P2, if one is slack, P2 to Pn. Here if it is the how much load buses, it is corresponding to this, because these are the vectors. Similarly, here R I am writing, means your equation number 1, what is this R1? You can see this this is R1 and R3 you can see here. This is, you can say this is R1, this is R2, this is R3, hardly matter. So, wherever you are writing, again just you have to derivate, you have to have the elements here written, but these three are equations. What we did, R1 just it is a fx is equal to 0, fx1, fx2, fx3. This is the same equation 1 and 3, just I wrote 1, 2 and 3. So, this was 1, remember this was 2, this was 3. So, here R1 and R2 again you can exchange, is up to you, but accordingly your these Jacobian elements will be modified. It is not that you have changed here and you are writing here derivating different one. Now, with this we are going to have some extra elements here and that corresponding to here your x dc. Because this is corresponding to, we are going to solve the 3 unknowns and the 4 will be specified. So, now again this matrix is going to be a square matrix. So, what we are doing, we are adding here the elements corresponding to this one and corresponding to this one. Earlier it was size was less, corresponding to only this. Now, we are adding the elements correspond here. There will be some elements, I will discuss what are those elements, and we are also adding the elements here. So, this is called your extended variable methods, that is in terms of your here in the Newton-Raphson polar form. Before that, let us combine the equation and I will come back and we will see what are the various elements. We require this reactive powers here as well for the rectifier end and your inverter end, because these QDR and QIs are required because we are writing the equations for the DC. Here what virtually we are doing, the DC equations we are writing, but the QDR and QDIs we are representing, that will come here, the QDR and PDR are the functions of this. Because this at any bus now, here this is your VTR. What happens? We are having so many lines, the AC lines, and we are having corresponding to your the DC. Means at this bus, if we are writing the power balance equation, means here I can say the P is specified, this PI here, it is your PGI. At this bus I am writing. So, I can write the R, not I here, oh sorry, PDR. This was your equation, if you remember, when there was no DC. It was equal to your, this is a function, I can say, or I can say PR is a function of V and delta. Now, I am complicating the function. It is nothing but, if you remember what was this, it was the summation of Vi Vj, j is equal to 1 to n, here Jij cos delta ij plus Bij sin delta ij. This was function, means it was a function of voltage and here angle. So, in simplicity here I am not writing this, I am writing here is a function of voltage and deltas. When there was no DC. Now, if I am going to have the DC here, means this is going to change. And you know the DC is equivalent to, we are going to take here some power here PDR and your QDR. So, if you are writing the PDR which is taking as a load, means this I can say it is just like a PDR if it is a rectifier. Mind it, what I did here, this is we are taking now including the DC. So, minus this is coming here because it is a load in the rectifier I am writing. Inverter it will be plus. So, this we are writing the expression here. I can remove this because we are not going in detail about this because the AC already load flow we have studied. So, here we are having this expression. Now, what is this? This is nothing but you will see this value is your specified here at that bus, because this is changing, how this depends upon is going somewhere. This power generation and the load here at this, because this is just like a line, this is going here and there. So, So, whatever here we are writing, that is a PGI minus PDI, this is basically specified power, that is we are what is generation, what is taken away, others are going here and there. So, this value is nothing but your PR is specified at this bus. That AC load you know, the DC load you do not know, because this depends upon the control mode, how much power is going, that is varying, but this value is known to you. Now, if you are taking this side here, this becomes minus, here this is minus, and this value already it was minus, here I can say PDR this equal to 0. Nay, what I did? This is your PGI minus PDI specified. This was that side, I keep this side is the minus sign. It was already minus here, we were subtracting. So, we are writing a equation that is Fx is equal to 0, which is a nonlinear equation we are to solve. In the AC Newton Raphson without DC, we solve this equation is equal to 0, remember. And this we want to put as some change in the P, this should be 0. That is a mismatch we always calculate, it should be 0, so that we can say we are exactly we are matching this here. So, this equation here you can see, this is written the equation here I have written the PTR now I am writing this AC here is written that we are taking at this converter end, this value is your here we are taking the PTR, that is specified, R is a rectifier terminal, basically this is known as a rectifier terminal, that is the AC. Here it is a inverter terminal specified I have written, and then minus this is your usual AC connected AC network, this is corresponding to your DC. Now, here in the DC we are having it is related with your this TR and the TI as well, we want to see whether it is related or not, and then X DC variables are there. Because your PD which is going to be there, it is a function of VTR, VTI and XDC. No doubt out of them everything, it may be only dependent on VTR, but we are writing in general, it will be dependent on your this terminal voltage of inverter, rectifier and some DC variables. Maybe other will be 0, but I can write in general it is a function of this. So, here I am writing this should be equal to 0. Similarly, if you will go here, it is the inverter basically. Inverter again we here up to this is a similar, because this is a bus AC bus. So, that is we are not considering the inverter, because in AC side there is no change, but here you can see here I have written plus. The reason is obvious, I explained that the power is going to the AC system. So, instead of this here it is going to be added, that is going to be injected in the inverter side. So, this is your plus, that is a PDI which is going in the AC system. Similarly, you can write for the reactive power at the two terminals, your this rectifier and inverter here, but in the both cases here it is negative, the reason both are absorbing the reactive power. So, already I explained, so that is here the sign is minus and minus. So, okay, this 4 equations we require, and then we can include this. Now, come here, if you see this QDR and QR, we have to write SDR square minus PDR, because we want now DC here the QDR as well. PDR already we wrote in terms of the DC variables, but the QDR here now we want to in the sequential method we are calculating the power factor. Here we want that we can write in terms of terminal voltage and the DC variables, so it will be easily accommodated, because there it was possible you are doing the sequentially, then you can calculate other variables. Here it is inside, because here the power factor is not a variable, it is not any variable here. We want this QDR in terms of your DC variables. So, what I am going to do now, you can say what is the SDR this equation. The here this power which is going here at this terminal, I can write this power which is going in the DC side here. What is the current going here? You remember it is your, I can write this is your this S dr will be your V at this point. Now, I am writing in the per unit. So, this into your IAC, which is going at this point, because this the voltage we are taking the same base here, the V into this value. What is this AC here? This is value we are taking, this is going to be inside. The current we are calculating in terms of the DC variable. Now, if you are taking this terminal voltage here, it will be here AR, TR here will be there, and this value will be there. This is a complex power at this bus now. Once you are having here, now you can put the value of IAC, we already derived in the per unit here, and if you are going to put this value, you are having why I want, because here the VTHR we want to be a variable here, that is already that's the function here, the VTH here will be appearing. So, this equation is also dependent on the voltage. So, we are trying to accommodate because it is extended, so that it should not be decoupled. Once you are having decoupled, means it is a sequential method. So, this your equation is having the VTH here, the voltage dependent on this here, and that is why we are relating here. So, we are trying to eliminate some of the few odd variables, and here we are writing in terms of this. So, the VTR should be there. So, here I wrote here this complex power at the rectifier terminal taken by the DC system, that is a converter. Here we can write here AR, this is rectifier OLTC, this is the terminal voltage where we are calculating this, and IAC, that is current going there. So, this value, if you are putting IAC value here in terms of DC, you are going to get, already we proved it here. Since we are writing in the per unit, mind it, this k term is appearing, again you are taking as a 1 or this, because now every base should be same. So, the current here you are writing in the per unit, this k will be appearing here, because now we are writing in the here complete this equation is written in the per unit basis. So, that is why here k is appearing, means here we are writing this AC in terms of per unit. So, this value is giving this terminal voltage is the AC. So, base is divided by the its rated value. So, there is no change. Similarly, I can write here for the inverter the complex power, here we can write in this form, and now the PDI and PDR are not in terms of the DC variable you can write. So, your this reactive power at this bus, that is your DC side, require the reactive power here rectifier, and this is an inverter, you can write in this fashion. So, you can put this value here, you are writing this is here, and that means you can say this is a function of VTS, here it is VTI and VTR is coming, and the DC variable as well. These are the DC variables already defined. So, now from this you are adding some more, and here we can write the mismatch factors if you are having two terminal AC system. Mind it, here in this case now we are going to discuss only the two terminal. If you are having the multi terminal, then whole the scenario you are going to write another equations as well, means we are assuming there is one rectifier, one inverter. So, we are having 4 equations, one for real power, one for reactive power. Similarly, we are having one real and reactive. This is for rectifier here, this is an inverter, the 2 equations. Now, so that is why here it is written, when the DC link is included in the power flow equation, only the mismatch equations at the converter AC buses have to be modified, means only at this point we have to modify. Now, you see in this P and Q, we were having the buses included, because in this here, if you are taking this is a VTR and you are having here VTI, these are the AC side and they are in the NRL of itself. So, they were here. Now, what we are going to do, and that is depending upon this x also. So, what we are going to do, we are going to write this equation to separate out the two corresponding to a rectifier inverter. This is the P, I am writing here the change in the P another one. Means now this vector, suppose you had the n bus, then it was your now n minus 1, because slack we have to not take. So, this is was this. Now, what I am doing, I am taking 2 again here outside, one for rectifier, one for inverter. So, now this is going to be your n minus 1 minus 2. So, this vector will be having Suppose you are having fourth bus is your rectifier bus. So, you are writing here on 1 is slack. So, you write 2, then 3, 4 will be not there, but there will be one inverter also. So, this is correspondingly you can take care. Similarly, here you are having the T is basically the terminal. The T is related to the terminal and it is HVDC terminal. So, you are going to have here the 2 elements, here again the load bus is minus 2 and here you are going to have 2. Means here I can say PQ minus 2, PQ buses. Now, this you are going to have 3 vectors, 3 elements, that is R1, R2 and R3 here. Similarly, here also we have to change. Here we are going to have delta T, the again angles at terminal of HVDC. Here also we are going to Vt divided by Vt, and this is there. So, now what we do, we just take out this one. The corresponding to this here, if you are derivating this, there is no AC, there is no change, mind it. But if you are derivating with this, the value will be changed. So, earlier whatever you are having this Jacobian, you can say J1, J2, J3 and J4, it will be intact. It will not change because AC side you are derivating, no DC variables. But if you are talking here, other than these 2 buses, if you are differentiating with this, it will be 0 because it is independent, it is a partial derivative. So, it is independent and it will be 0. Now, corresponding to this, with this it may happen and I can write here some element A. This is the matrix. What will be order of this matrix? 2 by 3.
2.
Because 2, this is your elements here, 2 by 3. Now, here it will be 0 corresponding to Q because other than these 2 buses. Here we can say it is your B matrix, it should be there. It will be again 2 by 3. Now, come here, this one with effect to delta. Have you seen any delta in the even the DC bus? It is including even here in this equation, it is no delta. This is not that delta, mind it, is not delta U plus alpha. This delta is the power angle of this. So, it is not there, so it will be 0. So, corresponding to this, even the both total here 2, it will be 0. Now, corresponding to this, it will be not here, but here it will be there because VTR and VTI is appearing. So, here I can write, so if you want to take it separate out, so I can write 2 here, 1 corresponding to this, 1 corresponding to this, 1 corresponding to here it is 0, 1 corresponding to here I can write E and 1 corresponding to this here I can say D. Okay. Any doubt? Because this is 2 and here XDC is 3. So, this element basically A, I will come that here you can see your A is the PT, this power at the terminal buses differentiated with this XDC. Here this is corresponding to this, corresponding to this, here we are not changing because it is AC side and there is no change at all. Only this, due to this PT, only the 2 terminals are appearing, this will be this, otherwise this will be 0, because the XDC is independent of outside these 2 buses. Only these 2 buses where the DC and AC are related, mind it. Other buses only it is AC and here is the AC and DC are there.
Dou R by dou V by V, why is it not coming? Because
Where?
del V by V and del Vt by Vt.
Huh, here we are writing the Vt also. No, del Vy upon V here writing, del Vt upon Vt we are writing.
Both correspond to the same rectifier bus, right, sir?
No, no, this is corresponding to a rectifier and inverter. This is a vector 2 by 2. is a 2 means is R means this is your del VTR. Oh, this is the basically this is del VTR y VTR one element, and another is your del VTI VTI. This is similar to this here we are writing this is earlier in the polar form. Same here we are dividing again. This is the same region, you remember it is due to the giving the quadratic convergence. That is why we are dividing. If you are not dividing, still you can solve this power flow, no problem. Only it will take larger iterations and sometimes it may not converge. But here by dividing this, the function why it is dividing already is explained in the first lecture. So that is why here the only what I did here, it was the voltage at all the PQ buses I have taken 2 out. So that is why here del Vt upon Vt we are again writing. To make it uniformity, because this otherwise Jacobian will change if you are not dividing here. We want this Jacobian should be as intact as the AC power flow, no change. Only these 2 buses we are taking out, and for this we are just talking here. So this D will be, you can see again I will come back, but let us see the basic principle here what we are doing. Now here as I said we are having in your these 3 equations we are having the 7 variables here, and that is why it is called XDC. So here with whatever is appearing here, this XDC is represented by the 7 variables here, and we are having only the 3 basic equations means 4 should be specified. So here it is written in the sentence the XDC vector is the internal DC variable, and the performance equation 1 to 9 involve the 7 DC variables we find. All these variables here already I have written completely here. Yeah. Equation 1 to 3 are independent equations, so we can use it, and this requires 4 other variables to be specified to solve this 1 to 3. So already I explained we require here this out of 7 we require 4 fixed and 3 we can solve it. So in normal operation what we do, normally the one terminal controls voltage, normally inverter controls the voltage and your rectifier controls your current. But again it keep on changing depending upon the scenario, and the control modes are changed. So here also if you are starting with one control mode, if there is some heating value here and there, voltage and terminal voltage are not there, then you have to change the control modes as well. Another here, that is here written, if the AC voltage at rectifier goes down, the rectifier may hit its alpha minimum value and then voltage controlled by rectifier, and the current here is shifted. The types normally it is not a continuous variable. However, here in whole this we are just solving as a one variable, and variable means it is not a discrete, we are talking as a continuous variable. But type cannot be, it cannot be in the several fractions. So what we do, first we take as a continuous variable, then we fix its near value, and then again we solve it and we see it. So the typings, even though in AC also, in the AC load flow also, if the OLTC transformer is there, so typings are taken as a your continuous variable, then we fix its nearest value and then we again solve it. So that is why here it is assumed to be continuous variable. Now come to the control mode, means we require 4 variables should be specified. Here you see if this inverter controlling the DC voltage, means here you will find the gamma is everywhere, means it is in CEA control. If here rectifier controlling the DC voltage, you will see the alpha R will be everywhere. No, alpha R, alpha R, alpha R, it will be, only the sequence is changed. Now here in this 7 ID I have written, here I am writing the PDI, effectively both are same. Here if the VDI is there, divide this is the current is known. So basically from the VDI you can calculate the current here. So it is the PDI is ID is almost same, and then that can be taken. Because in the DC link what we do, instead of knowing the current, normally we know the power more variably, how much power is flowing here and that end. So it is taken, this ID is basically related with this PD. So the PD is everywhere, and this is one of the, this power is fixed, that how much power you are flowing in this link, and then remaining you can calculate the control modes basically, because power normally is set in the DC link. This is the beauty, this is how much power you are setting. If you have power you are keep on changing, you can change the different power and you can again calculate the DC variable. So, you can see this is ID is everywhere, I can say, and others are here alpha, gamma, VDI, all this here the fix, the various control modes, normally we call the 7 control modes are there, and then means if these are the possible specified variables, remaining are to be calculated. For example, if you are taking the control mode C1, here what are the unknowns? Here one is your VDR, VDI is there, ID is there, alpha R is there, means your AR is missing, gamma is there, means AI is missing. So, we have to calculate your AR, AI and means here we are requiring this and VDR. So, this 3 in that control mode should be calculated from there. Now, let us see now again how this HVDC is operating. You know, there is a various option, as I said in the system here, there is a possibility that this system is having a AC line and then you are having a DC line parallel to this, or you do not have and it is connected in the AC system here itself. Means option A, that you are having here the no AC line parallel, means you are having this type of somewhere in the inside the complete synchronized system it is there. Another, there is a possibility you can have the parallel direct AC line. Another option that here the two systems, independent systems are connected by the DC system. They are operating with the different frequencies. So, the 3 scenarios can be there inside the AC system, or it is the 2 different frequency systems are there. Now, if the 2 different frequency are system there, so they must be solved separately because they are operating at the different frequencies. So, it is just here what is the P and Q, and here also is the injection, and you can just solve it. But if it is inside embedded, then you require AC DC system combined together. So, for this type of, as I said, 1 and 2 options, now we are going to modify here. One is there, so independently you can solve it without any problem. Now, you can see here what I have written, it is I have written here, you can see. Instead of here B, it is C is written, the reason C is more convenient because B looks like the B of Y bus matrix. You know, if you write here Y, it is your G plus JB. So, to avoid the confusion, it is better to write C. So, that is why here C is used, nothing else. Here J1, G2, sometimes people write here H and JL in some books you will find. So, purpose is here this H is your J1, here is the J2, here means this is a derivative of your real power with your delta. This is your real power with respect to voltage, here reactive power with respect to delta, here again the derivative of your reactive power with respect to voltage. So, these are here you can say same, and now here you can say already I have written 0, 0, 0 here, again here I have written D and E. So, we have to write here D and E, so that already I have written equations corresponding to that. So, otherwise we have to change. You can give any name, but again if you are writing D, so it will be again now what will be order of this matrix? It is 3 will be sure because R is corresponding to this 3 cross 2 because this is corresponding to this and this is 2. This will be 3 cross 3 because this corresponding to this derivative with this. So, here you can find this, you see now these are the value here with that notation. Now, you can see this is a actually this is not so proper, I think there is some change, it is a partial derivative, it is not del. So, you can change it here. So, you can see here the D, E and other values are written here, and these are the matrices, means it is a some order of matrices and these should be calculated. Now, for given here, suppose you are taking the control mode A, or I can say C1. Now, your these variables are specified, means you have to calculate this 3, as I said here the 3, and then you have to, if you are writing R1 to R3 here in this fashion, if again you can change R1 R2 anyone depending upon yourself, then we can calculate these values for matrices. So, here now first I will calculate this E, that is a square matrix very simply, right. Now, this is nothing but you can see this R here, we are just differentiating with R to XD. Now, again here X, what you are denoting? X, if you are writing in this fashion, if you have dr, AR and your AI, then accordingly you have to differentiate it, means this is your XDC 1, here XDC 2, here XDC 3. Or if you are changing, then you have a matrix and this will be always consistent. So, you have to decide R1, R2, R3, you have to decide this unknown variables accordingly. So, what I have decided here, I am saying this is AR, means I am writing in terms of this, then it will be your, what will be XDC, I am writing in this way. This is the vector should be calculated. That is why here it is written. Now, if you are taking R1, R2, so this E element here E, we are having this, I can say 3 cross 3. Now, R1 is to be differentiated with this here. So, if this is R1, if you are differentiating with AI, what will be this value? 0, is a partial derivative is independent. If R1 is differentiated with AI, if differentiated with this one, is not 0, is minus 1. Now, if you are differentiating with this, the R2, this is 0, here we are taking the term. Here his k is appearing, here not k1 is the k basically. Yeah. So, this here the differentiating, you are differentiating, you are this k VTR cos alpha r is appearing. So, you are getting k, this is your VTR cos alpha r, what plus? This will be 0. No, this is alpha, we are taking a, it is a basically. It is a, actually it is a typing mistake, it is the alpha and a, basically it's slightly confusion. So, this is your A, this is your AI. So, this will be 0, we are getting this value. Now, if you are here 0, next with this VDR again minus 1, we are going to have minus 1. Now, 3 here, this with alpha AR 0, here we will get KVTI cos gamma I, here 0, VDR not VDR, yeah. So, you can see these elements are calculated. So, only you have to see that you have to sequence your XDC, you have to write this and it should be throughout the same. It is not that you have to exchange here and there because these elements will be getting modified.
So, before solving this, before forming the matrix, we need to know the which control mode it is working.
You need, yes, because then you, otherwise you cannot fix the 4 variables. So, it is will given to you, this is the control mode in basic it is operating, then means these variables are fixed, it is known to you and then you can calculate this.
So, these are dynamically changing, sir?
Yeah, it will be keep on changing if it will be hitting some limits, because let us suppose your tap is hitting, you are calculating tap is coming something absurd, you have to fix that value and this is fixed now, tap is known, then it will be going in the different control modes. So, it is basically keep on changing like your PV and PQ buses. So, here also it will be keep on changing and then we can calculate the E and similarly we can calculate others and we will see in the next turn again and then we will go for the variable elimination method, that will be end of this AC/DC load flow. Thank you.